This is 1979 IMO problem number 6. Here is a view of this problem. We have a frog which starts jumping at the point A, and it would like to reach the point E here on the opposite side of this opposite vertex of this octagon. And the rules is that starting at point A, it can either jump to point H or to point B, and so on. If you are at point B, you can further jump to C, or you can go back to A, and similarly. So at the least, we can easily observe that it would take the frog at the least 4 steps to reach E, right? So, but that's not the question. Well, it is kind of the question. It's asking how many distinct paths are there of reaching point E starting from point A in n jumps. So capitalizing on our observation, for example, it would not be surprised to see that A sub 4 starting at point A and going into E, how many ways, taking only 4 jumps, can we reach point E starting from point A? Well, on our octagon, we can either go clockwise or counterclockwise. So we have really two paths leading to point E starting from point A in just 4 steps, right? So we have really 2 paths. Indeed, anything less than that is impossible, right? So A1, A2, A3 is indeed 0. Does that make sense? How about A5, for instance? Can we ever reach the point E in 5 steps? Well, obviously 5 steps means an odd number of steps. So starting from point A, let's assume without loss of generality that we went that way, the clockwise way. Obviously 4 steps, I shouldn't reach point E, because once I reach E, I need to stop. So it means that because I cannot directly go to E, at some point I need to go back. And once I go back and move forward, it will take at least 6 steps. So it's impossible to reach point E starting from point A in just 5 steps. So therefore there are 0 paths to reach E starting from point A in just 5 steps. And in fact, indeed, it's quite easy to confirm that it would be also impossible in 7 steps or 9 steps or any odd number of steps. The best way probably is to figure out an invariant, and I would be most happy to give you a hint. You can probably number the vertices in binary, and I guess every odd number of steps would lead you to the same binary, which would be a binary vertex which would be different than the vertex E. For instance, if you label A, C, E, G as 0 and B, D, E, F, B, D, F, H as 1, I claim that every 2 steps starting from point A, well, or let's say for starting from point, let's say D. Well, it doesn't matter really, but you would see that invariant, the fact that odd number of steps only end up at a vertex with a binary label of 0, right? So it's impossible to finish it in an odd number of steps. The real part of this question is really the second part, which is kind of to prove this closed form. The best way to solve this problem is arguably to set up a recursion, but for the recursion I will do the following trick. Well, I know how A sub n is defined, so A sub n is the number of distinct paths starting from point A going to point E. But why don't I just extend this definition? For instance, why don't I say B sub n would be the number of steps or sorry, number of distinct paths, I should say. Sorry for that. Number of distinct paths of exactly n jumps, but the critical thing is starting at point B. In a similar way, I can describe C sub n, number of paths, distinct paths from starting from C to E. Does that make sense? So the previous one was also starting at point B and to point E. Okay. And so on. You can clearly describe D sub n in a similar way. Notice that I'm only worrying myself on one half of the octagon because there is a pure symmetry in this picture, right? So therefore it would be I will exploit this symmetry in just a minute, right? So the number of steps needed to complete the task to reach E, if you start on point C or G, is equal actually, because those two are symmetric with respect to point E, with respect to the final destination. So those two are also symmetric. Does that make sense? So therefore B sub n should be exactly H sub n, and C sub n should be exactly G sub n, and so on. D sub n must be equal to F sub n. But let's go back to our logic. So we decided the best strategy would arguably be to set up a system of recursions, and for that I will personally focus on two of the vertices, vertex A and say vertex C. C and G are obviously symmetric, so we can handle that pretty easily. So if we start at point A and we take two steps, what can happen? So A sub n, so let's start with this. So remember, A sub n is the number of paths, distinct paths, starting from point A to point E, going to point E, and finishing this in n steps. Now, we have really two cases. Either starting from point A, in two steps, I will go to B first and then come back to A, or go to H first, come back to A. So that's the first case. There are two ways to do that, right? So so 2 times, and then once we are back at A after 2 steps, well, it will take, I will have now n minus 2 jumps left to accomplish the task. Or I can start at A, I can make 2 jumps forward, and so I can end up at C, or for that effect I can end up at G, but it doesn't matter. I'll just multiply everything by 2, at which stage, and once you're at point C, you have only n minus 2 steps left, and we already have a definition for the number of paths, distinct paths from point C to point E in taking n minus 2 steps. So therefore, no surprise, we have n minus 2 steps starting at point C. That's just C sub n minus 2, and that's it. That's the first recursion. Now the second recursion, so C sub n. So this one is a little bit tricky. Obviously, if you start at C sub n, you can win this. You can stop in, for instance, if you want to calculate C sub 2, right? So let me make note of that. So C sub 2, oops. So how many paths are there starting at point C, going to point E, in 2 steps, in 2 jumps? Well, there's only one really. It's C, D, E, right? So this is really one way. Does that make sense? Okay. So let's start the recursion at C sub n. The trick here is that consider all the distinct paths starting from point C to point E in n steps, but with the condition that n is strictly greater than 2. So that will eliminate the possibility that we will go directly from C to E. And so now the recursion becomes, with this additional restriction, well, starting at point C sub n, because I don't want to directly go to E, I can either go to B and then come back to C, or go to D, come back to C. Well, those are equivalent, so 2 times. And because I wasted, sorry for that, so that this can happen in 2 times, after which I have n minus 2 steps, because I already wasted 2 of my steps. So which is C times n minus 2, plus, or starting at point C, I can totally mess up. I can totally go back all the way up to A, which is totally opposite E, right? That's not good news for us. At which step there's really n minus 2 more different ways to go from A to E in just sorry, there is a sub n minus 2 ways to go from A to E in n minus 2 steps. So this is a sub n minus 2. I hope that makes sense because we're pretty much done. So we have our system of recursions. Obviously, I need a few initial boundary conditions, which I have already given. For instance, this one here. Obviously, these are also nice, but probably the most useful one in that class is this one. And I also have C sub 2 is equal to 1, which I can also make use of. So what to do next? Well, how do we establish, how do we prove that A sub 2n is indeed equal to what is dictated by this system of equations? So let's further simplify this system of equations into one unique equation, one unique recurrence relationship. Obviously it would be the best if we can express a recurrence relationship for an. So somehow I need to get rid of these C sub n minus 2 expressions. Okay, so what we can do is, hey, look at that, both expressions have these two. So what we can do is we can isolate these two. So this implies that from the first one we have a sub n minus 2 times a sub n minus 2. That's equal to c sub n, oh, sorry, 2 times. I should say 2 times c sub n minus 2. Or from the second one, I would get, because I want to isolate this guy here, it would be c sub n minus 2 times c sub n minus 2. And that's again equal to 2 times c sub n minus 2. Oh boy, I'm high. That should be really a sub n minus 2, right? Because I just took that one to the left-hand side. But that's it. The right-hand sides agree, meaning the left-hand sides should agree as well, suggesting that, for instance, let's express everything in terms of Cn. So Cn would simply be equal to, we still have this guy on the other side, and then we send that one to the other side as well. That will go as a sub n minus 2. There's already minus 2 a sub n minus 2. So therefore, final outcome is a sub n minus a sub n minus 2. At this stage, I will make the following trick. I will use the shifting trick, shift. The reason is obvious, because I want to substitute back into one of these equations, and really that shifting trick will help me. Well, shifting trick means replace, substitute n with, let's say in this case, n minus 2 is what I'm interested in. Look at this expression. I really need that one actually. So n minus 2 minus a sub n minus 4. But now let's be careful in that occasion, because previously we needed n strictly greater than 2. Now it seems that we need n strictly greater than 4 now in this expression. Now it's time to replace these two and substitute it into the first equation, say, right? So therefore a sub n is simply equal to yeah, so 2 times a sub n minus 2, and then I add these. Obviously there's a 2 coefficient 2 in front, so I need to be careful about that. 2 times a sub n minus 2 minus 2 times a sub n minus 4. Finally, that's equal to a sub n equals 2 more. I have 4 times a sub n minus 2 minus 2 times a sub n minus 4. That's a really awesome expression, but remember, it only works for n is strictly greater than 4. Claim that this recursion uniquely defines the sequence a sub n sequence, because we already, if we combine this recurrence relation with the earlier initial conditions, that for example a sub 4 is 2 and a sub 1, 2, 3 is 0. Let's make use of this. where let's write that, where a sub 1 equals a sub 2 equals a sub 3 equals 0, and a sub 4, finishing the game starting from point A to point E in 4 jumps. How many distinct paths? You can go clockwise or counterclockwise, so there's really 2 different ways to accomplish that. So combining our recurrence relation that we have just found with these initial conditions guarantee us that this sequence describes a unique sequence A sub n. Yeah, so therefore the only thing remaining is to verify that indeed this solution A sub n, so this really messy solution, well, it's kind of tempting to just replace these two with u and v, I would say, right, which we will do next, hopefully in a few minutes, right? So so we need to really verify that this solution indeed satisfies these conditions. So well, obviously A1 and A3 being 0 is no big deal, because we already knew that it's impossible to finish in an odd number, and this recursion only works for A sub 2n, obviously. So all I need is to test A sub 2. Let's see if we can get A sub 2 equals 0 in that formula. So I have replacing, in order to get A2, I need n equals 1. So therefore n equals 1. You substitute this, you get A sub 2 equal to 2 plus root 2 raised to the power n minus 1, but n is just 1, so this is raised to the power 0 really. So let's factor out the denominator, obviously. So as we said, 2 plus root 2 raised to the 0th power, or 1 minus first power, minus 2 minus root 2 raised to the 0th power again, right. And so therefore this is just, obviously these two terms are both equal to 1, so these would vanish, and wow, that's pretty convenient. How about A4? That's 1 over root 2. Okay, let's be careful again. 2 plus root 2 raised to the power, okay, so because 4 is 2 times 2, remember our formula was 2n, right? So it's 2 times 2. So therefore it is the power would be 2 minus 1, right? n minus 1, remember the formula. And this one is 2 minus root 2, 2 minus 1 again. And finally this is 1 over root 2, open brackets, 2 plus root 2 minus 2, minus minus would be plus root 2. And that's pretty much it. The 2's cancel out. We have 2 root 2 inside the brackets. Divide by root 2, we have just a 2. And boom, we have already confirmed these two results. Compare it with the initial determinations that we had. Only thing remaining is to show that this, again, the same recursion, this one, satisfies this one. So that would be really nice. Sorry, I should have said the given closed form solution satisfies this recursion. If I can show that, because this recursion uniquely describes the sequence A sub n, then obviously this formula, which also uniquely describes a sequence claimed to be A sub 2n. So what I will do is, let's write this, but I will rewrite it as A sub 2n prime. 1 over root 2, the one above, right? So the one given in the question, in the problem, I made a small modification to it. So minus 2 minus root 2 all raised to the power n minus 1. And now let's see if we can show that indeed this thing describes this recurrence relation, or this recursion. Obviously there's a mismatch in terms of the indices, so let's first fix that. So therefore we can change this condition as A sub 2n equals 4. Does that make sense? A sub 2n minus 2, right? So because I have just substituted n with 2n, minus 2 times A sub 2n minus 4. I hope that's clear. Okay, now we can go ahead and and see if this indeed, when I plug this whole expression into this polynomial, will this recursion will give me the same result. This will be really bashy. I hope we can pull that off. But really, life should work out really beautifully. Let me go ahead and actually now use that strategy. Let's call this guy as U, that one as V. We can do the following. So because you might think, hey, when I substitute this whole thing into this expression, okay, let's just plug in this huge expression into these three parts. In fact, let me move everybody to the left hand side. So really what we are, a sub 2n minus 4a sub 2n minus 2 plus 2a sub 2n minus 4 is equal to 0. Are you guys ready? Let's see if we will. So this term is 0. Let's see if when we plug in all these expressions we can get to 0 as well. So as I said, 2 plus root 2, 2 minus root 2, I will replace them with u and v. So substituting in, I get 1 over root 2, and I have u to the power n minus 1. I'm substituting into this one first, minus v to the power n minus 1 minus 4 times, again, 1 over root 2, u to the power n minus 1 is now n minus 3, I want to say, because the 2n here is replaced with 2n minus 2. So therefore, oh, n minus 1 it will be, right, half of it. So which means it will become n minus 2. Sorry for that. U to the power n minus 2 minus v to the power n minus 2. And I'm finally adding back 2 times 1 over root 2, u to the power n minus, well, I guess it will be 3 now, minus v to the power n minus 3. And let's see if this makes sense. Well, 1 over root 2's I can easily see will go away. And look at that. Looks like, do you guys agree that we have, we kind of have two different expressions, one in terms of the u's and another one in terms of the v's. So I can just kind of split them. Does that make sense? So, in fact, I will do this. So u to the power n minus 1. Well, okay, let's do it in 2 steps. Minus 4 times u to the power n minus 2 plus 2 times u to the power n minus 3 is equal to v to the power n minus 1 minus, yeah, plus, and then minus when you send it to the other side, I guess. Right. Yeah, that's right. That's right. Yeah. 4 times v to the power n minus 2 plus 2 times v to the power n minus 3. And at this stage, now it's clear what we need to do. It looks like both the left-hand side and the right-hand side has the same shape. Indeed, they both look like a polynomial, where the polynomial is substituted with a u here, and the same polynomial with a v. And we are checking to see if those are, under what conditions they can be equivalent. And indeed, our polynomial is xp of x equals x squared, well, x to the power n minus 1 minus 4x to the power n minus 2 plus 2x to the power n minus 3. And then I can, well, yeah, I can factor out n minus 3 out, so x to the power n minus 3. What I will left here is an x squared minus 4x x actually, because 1 here and n minus 2, it will become n minus 2 plus 2. And boom, that's it. So obviously this is useless, redundant, but look at that. What are the roots of this polynomial? Well, indeed, if you set it equal to 0, this whole thing will have roots at 0. Or look at this. 0 is out of our range, right? So we are not interested in, well, okay, so it doesn't matter really. But look at this one. When I look at the roots, so x1 would be minus, so it will be 4 plus, let's say, square root. So b squared is 16 minus 4 times 2, which is 8, all divided by 2. And x2 is the same expression except with a minus sign. But that's simply equal to 4 plus 2 root 2, but divided by 2 is 2 plus root 2. Let's call this just x actually, and y would be 2 minus root 2, and boom. Wow, so isn't that amazing? So indeed, our u and v are the roots of these polynomial expressions, and because they are roots, they will both make these expressions equal to 0, and as a result, they will, right, so these will be equivalent expressions, and the desired result is proven. So indeed, this prime, this solution, right? So we needed to show that this is a solution. So when I replaced it with a prime, I realized that it satisfied the same recursion, this one, that I have obtained by just using simple logic to solve this problem, right? So the two are equivalent in that sense. Just a few quick notes. I would like to make a few remarks here, which I claim are kind of important. So a few remarks. Well, one of the remarks is it's kind of disappointing that this expression is given to us, the solution, and one wonders if we could have gotten that solution, namely a sub 2n equals 1 over root 2, that's expression, which let's just call it u here, n minus 1 plus minus v n minus 1, where u and v are 2 plus root 2 and 2 minus root 2. So it's kind of disappointing to see it's given. So can we obtain the same thing using the recursion relationship that either this one, this or these two? Well, the answer is yes, but it requires first year college linear algebra background for that. It's not too hard. So you just have your you need to use matrices, kind of like transition matrices, and you need to calculate the characteristic polynomial, and from there we can find the eigenvalues and the eigenvectors, and those would lead to the desired solution. But as I said, because the topics of differential equation and linear algebra are mostly for college students, for freshmen and sophomore college students, so that's why I will just skip that. But secondly, I have two open challenge questions for you. Well, it's really not open questions. It's, I mean, yeah, it's just nice questions. So, what are my questions? Oh, yeah, I remember. So the first question is this. Obviously, the question was asking how many paths from A to E in a certain number of jumps. Well, one question would be this. What is the expected number of jumps this frog has to make starting from point A to reach point E? So what is the expected number of jumps? Expected number of jumps. We know that eventually the frog should be able to reach the point E, right? So, but the expect number of jumps from A to E, that would be really cool. So if you can calculate this, and if my calculations are not mistaken, I think I found, I did find 16. It's kind of remarkable, and so I claim that you need in average 16 jumps to reach to the point E. Well, the least number of jumps is obviously 4, the max is infinity, but in average you will need 16 jumps. Now the second part of the question is that, well, this is the first question, Q1. Let's see if you can use the comment section at the bottom sorry for that, to make a discussion. But the second question, Q2, is again an expected number of jumps, but what is the total number of jumps, expected number of jumps needed, let's say from the point A, starting from point A, but this time to reach all vertices of this octagon, right? Obviously, we have already, because we start at point A, we already discovered one of the vertices, so there's still 7 more vertex to discover. Now the question is, how many jumps it will take us in average to discover all the vertices. And again, if my calculations are not mistaken, and as I say, I make a lot of silly mistakes most of the time, I think the answer should be 28 jumps. So let's see if you guys can solve this. You can use the comment section at the bottom, and maybe in a few days, if I have time, I would love to shoot another video where I can provide the solution to these 2 questions, or maybe some people will just make the description at the bottom under the comment section. So yeah, I hope you enjoyed this video. Sorry, I mean, sometimes when I watch these videos, I usually watch them in fast speed. On YouTube you can choose the speed for which you can find. I usually find myself watching myself again at the optimal speed of 1.25, and you can even try 1.5 if you feel that my presentation is very slow. Okay people, I hope you enjoyed this, and looking forward to see you guys in our next lecture.